So we were talking about flatness, and if you remember, we had a quick brush up of tensor products, and then this note has been shared with you. Very sorry that the initial scanning was actually too big in size, and you had difficulty in downloading it. But today I'm going to straight away share the PDF created from this iPad. So, and that will be a lot easier. Okay, so this is what we talked about. If you remember this symbol, this E, this symbol of this E stroke T will always be the exercise stroke tutorial, so that you can, if there would be some gap and you would have to fix it. And if you do not manage, then like tutorial session would be the platform to discuss. And also you can post these questions on the Google Classroom and somebody will answer. So that is how we would like to go about it. Okay. So these are certain things we have already talked about, and some word of caution. And if you remember, this 3 was in fact, uh, I can see that there is a slight delay here. Okay, so probably because it's a PDF. So then we talked about the flat modules. We gave the definition and these propositions. I'd like to draw your attention to this corollary. This corollary is something which we have sort of discussed. But this corollary, if you remember, we had to prove one proposition on faithful flatness. And this is the corollary which is actually going to be of much use. Okay. So let me first do that quickly, and then I will move on to the next phase of my talk. Okay. Yes, so just to recall the definition of faithful flatness. Second, please. There is a bit of a delay for some reason. Yeah, so the faithful flatness is, this R module is faithfully flat if it is flat, and whenever you have this tensor product equal to 0, for an M module, for an R module M, then that module M is 0. Okay. And the ring homomorphism, now this is the definition which we will be using very often today, that this ring homomorphism phi from R to R dash is called faithfully flat if R dash viewed as an R module is faithfully flat. Okay. So we will be talking about base change and quite a few things, and also the faithfully flat descent, where this is the one which we will be using very, very often, this terminology. Okay. Now, this is the proposition, let me take you to the next proposition. This is the proposition which I didn't have time to complete. So this was the statement that if you have an R module N, then these following statements are equivalent. What are the statements? One is N is faithfully flat, then N is flat, and given a morphism of R modules phi from M dash to M, such that if you have this the tensorized this function is the zero morphism, then phi will be 0, and then a sequence of R modules M dash M double dash is exact if and only if after tensoring this remains exact. So you know this the faithfully flatness is playing a role here to to infer that when you have the flatness, then you know that after tensoring you have the exactness. Now how to go about, that is the main thing. Okay, and we will in fact continue with this discussion in the case of faithfully flat modules. Actually, this is what we call the descent. Okay, whether we can go back to the original thing, retaining the properties is a very important concept. And finally, N is flat, and for every maximal ideal M in R, we have Mn is not equal to N. So all these 4 statements are equivalent. Now these statements, proving these are not difficult at all. Let me just, instead of going line by line, let me just show the main parts which you would be using. I told you, right, that corollary would be of much use on the kernel and image and things like that. So this is exactly what we are using here. So let me just read out the first part, that N is faithfully flat, suppose, and phi is a morphism of R modules, M dash to M. Then phi is 0 if and only if image phi is 0, obviously, right? So if you would like to know that you are proving 1 implies 2. So that means you want to know that this, if you know that the after tensoring this is the zero morphism, then whether you have the original map is a zero morphism. That is exactly what we are trying to prove, isn't it? So therefore, you are trying to show that image phi is 0, but you know that image after tensoring, this is image of phi tensor, the identity function on n, but this we have already established that this is image phi tensor n, okay? And that is 0, right? Once you know that that is 0, and therefore you have that everything, I mean, like image phi is 0, etc., etc. Okay, so that is coming from the faithful flatness of n. So 1 implies 2. This is how you prove such a thing. This is a kind of a very standard procedure. But do remember that corollary is being used here. Okay, since I have not numbered them very nicely sequentially, maybe I'll do it in the formal notes. So therefore, I don't have a name to call it, but you know which one I'm talking about. Then when you are proving 2 implies 3, that is, suppose 2 is given and you want to show that given any such sequence of R modules, after tensoring also it remains exact, and conversely. So that is the most important part, right? So flatness would take care of the exactness after tensoring, but you have that you have that after tensoring, if it is exact, then how do you go back to it? That is the main thing. So therefore, if you already know that if you have a sequence here, so let me again read the most important part of this proof. So a sequence is exact if and only if we have that image of phi psi composition phi is 0, and that the canonical map is 0, right? So therefore, given 2, this is equivalent to saying this image is 0. Now, once again, you see, you have actually the sort of reformulated it in the form of this some kernel image, and then you are using that same fact that you know that this is true, 2 is true. That means what? That means that n is flat, and it is given that this is the zero morphism. So this is the zero morphism. If this is the zero morphism, then phi is the zero morphism. Okay, so therefore you have a way to sort of take the tensor out. So you have some statement, some hypothesis given after tensoring, and you know how to get rid of it. So that is what is being used here. So if you just follow this a little carefully, then you will see that by exactness, you have image phi equal to kernel size. So after tensoring, it remains unchanged, etc., etc. And then this is how you prove the 2 implies 3. And then 3 implies, we go about 3 implies 1, 1 implies 4. Okay, so essentially the same thing. I mean, like, I think you can, if you have had a look, then you would immediately understand that every time what is being used here is that since you have a faithfully flat module, therefore tensoring is 0 implies that module, the other module should be 0. That is it. That, see, in 1 implies 4 also, it is the same old thing which is being used every time. Now for 4 implies 1, where you have a statement using the maximal ideal. So this is 4. So you want to show that 4 implies 1. So what does that mean? So n is flat, that is given to you. And for every maximal ideal M of R, we have that Mn is not equal to n. Okay. Given this, you can show that n is faithfully flat. What does that mean? Therefore, you want to show that if n tensor M is 0, then M must be 0, right? Because flatness is already given to you. Now, how does it follow from this statement about the behavior of n with the maximal ideal? Okay, so this is how you go about it. Once again, that this you know that, yeah, sorry about it. Yeah, now it has come. So you know that this, look at this part, that n mod mn is actually isomorphic to n tensor R mod m. And this is non-zero. I think I have missed that part. Okay, for all maximal ideals. And then we show that this m, if m tensor n is non-trivial for every non-trivial R module m, then I mean, like, see, if you want to show that if you have the tensor is 0, then you want to show that the module is 0. So you just sort of say that the other way around. So that means non-zero and that it remains non-zero. Now, how do you go about this non-zero part is that you just, so what you do is the following. Let me just quickly go through it. So what you do is, so let n be a non-trivial R module and x be a non-zero element. And now look at this cyclic submodule. And it's a one generated submodule. So you have this epimorphism, the surjective R module map from R to M dash, okay? And the kernel will be some ideal. So this is what you have. M dash is isomorphic to R mod A as an R module, correct? And now this inclusion gives a monomorphism after tensoring, this part, because n is flat, that is given to you. And this is isomorphic to this. Once again, n is flat and M dash is isomorphic to R mod A. So therefore, you have this sitting inside M mod N, M tensor N, I'm sorry. So therefore, to show that this is non-trivial, it is enough to show that this is non-trivial. That is, this R mod A tensor N is non-trivial. Now, R mod A is isomorphic to M dash is non-zero. That is because you have started with M dash is the cyclic submodule and generated by a non-zero element, correct? And now A is a proper ideal, right here, because here you have A is coming as the kernel of this map, okay? And there exists because otherwise it will be the zero map, right? It will be the zero module. Okay, now there exists a maximal ideal because it is proper. You have a maximal ideal containing A, and now you look at the commutative diagram and you know that non-zeroness after tensoring by R mod M, and therefore you have the non-zero property of N mod AN, okay? So this is like the, so every time you're using the flatness condition and also the diagram chasing, a bit of diagram chasing. Okay, so now let me move on to.
Sir?
Yes, just a minute, please. Okay, just if once again, you please tell me first whether you need it bigger or not. So then, is it okay? Is the size okay?
Bigger will be better.
Bigger will be better. Okay. Now, is this better? Here, probably there is not much delay. Is this better?
Yes.
Fine. Okay. Yeah. Yes. What is the question?
Yeah, sir. In the equivalent statements, does the second condition necessarily mean that the faithfully flat module is giving a faithful functor?
A faithfully flat module is giving a faithful
Functor from A mod to A mod. Means if M is a faithful flat module, then tensoring by M is a faithful functor, something like that.
You mean the left exactness and the right exactness both are being satisfied, right?
Yeah, no, I am saying for the faithfully flat module, what you enlisted in the second condition.
Yes.
So does that imply that tensoring by a faithfully flat module gives a faithful functor and vice versa?
What do you mean that the zero condition?
Yeah, home xy to home fxfy, this is injective.
Yes.
Okay, so that is the reason behind the name.
Correct.
I think.
Yeah, well, okay. So you had that question. What is the reason behind that name? Yeah, you could take that as a reason behind that name. Okay. But I'm not very sure still, okay, whether it is a completely categorical language or not, or there is a geometric motivation. Yeah. Okay. Yeah. Because which came first is always an issue. Okay. Should I move on to the next part? So this is fine. Is this okay?
Yes.
Okay. So this is about extent. I told you, right? We will be talking about this extension of coefficients means if you have a ring homomorphism. So that is exactly when you say that R dash is an R algebra. So now what we mean by extension of coefficients is that if you have so let me read just the first part because that is important. An R dash module, if you have an R dash module, okay, R dash is this ring, then that can be viewed as an R module via phi. So phi is the ring homomorphism. So I have just left it as an exercise. This is an obvious way to look at it. You know what it means actually. If you take any element from R, then you just take phi of A. Now you have the R dash module structure defined on N dash, and therefore you can define your A dot X as phi A dot X. So that is exactly what we mean. Okay. So now we say that the R module structure on N dash is obtained by restriction of coefficients with respect to phi. So in particular, R dash is an R module because if just in place of N dash, you take R dash. So this is fine. Okay, so now if you have an R module, then you have a natural way to, once again, when I'm saying natural, when I'm saying canonical, I mean to say that I will be able to establish it using the universal property. So that is the meaning that we understand, okay? So if we have an R module, then if you take the tensor product with respect to R dash, because R dash is an R module, obviously. So then this makes sense, okay? And this is an R dash module. Now, see, this going through these proofs actually is probably not essential, but I want to just sort of show you the main part which you should always be careful about. The moment you are trying to define a map, when you have this kind of quotiented objects, okay, these are, you know, I mean, like you always be thinking of the universal property, nothing else, no brute force. So what do you mean by saying that you want to show that it's an R dash module? So that means I should be able to give a map from R dash cross this to this, right? Isn't it? So how to go about it is that you first define this R bilinear map, because you know what it means by saying that to give a module structure, you have to give from R dash cross this, and you have to give make that separately linear, isn't it? So there is some message. Let me have a quick look. Yeah, okay, sure. Okay, so so if you want to give that, then so let us first see what this is. So if you fix an element A dash in R dash, then you can immediately give this map going this X comma B dash. There is no harm in defining this map. There is no challenge. That is taking this to X tensor A dash B dash. Okay. Now this induces, now it's easy to check that this will be bilinear. That is from the basic properties of tensor product. Now this immediately induces the R linear map from M tensor R dash over R to M tensor R dash over R. The moment you have an R linear map, right? So therefore, and they see how you have defined the R linear map, that you have defined for every A dash in R dash. So that means for a fixed A dash in R dash, you have a linear map, and that is R linear. So therefore, you can naturally define that scalar multiplication, what we call, from this R dash cross this M tensor R dash to M tensor R dash, okay? So this is kind of, once again, I mean, proving this is of course easy, but once again, the main part is that you use universal property and nothing else, okay? So therefore, you can define this. This is going to be your definition, but the validity of this definition is going to come from this. That's the main part. So which define this as an R mod dash module, and we say that this is obtained from M by extension of coefficients with respect to phi. So this is extension. So naturally, if you have a module over R dash, you have a module structure over R. If you have a module structure over R, then how to go to module structure over R dash, and that is by tensor product. Okay, good. So now, okay, so I have a couple of quick and easy observations. I hope it is visible clearly. Yes, still there is a bit of a delay. I can see that. Okay, so you have
Can you go to the previous page for a minute?
Should I go to the previous page once? Sure.
Yeah.
Yes. Yeah, it is still kind of taking some time. Please wait. I don't know. I think it is because of the connectivity. Yes, yes. Tell me.
So when you said that M tensor R dash makes sense.
When
Okay.
I say this,
Okay, I understood. Fine, you can go. Sorry. Yeah.
okay. Yeah, I can't help it. Actually, there is a bit of a delay today. Yeah. Okay. So let us start. So these are some very simple observations. I would say E stroke T. Therefore, you can settle it yourself that if you have a ring homomorphism and M is an R module, okay, and if you have a generating set for M over R, then after tensoring it generates, kind of obvious. And if you have a free generating set of, so M is a free module over R with this as a basis, then this will be a free generating set. This also you can easily prove, okay. Now this lemma is something which is going to be of much use and a very, very important thing. So I have thought that it's probably good to give a name to it. So we call it a base change lemma. So that means if you have this three rings R, R dash and R double dash, and if you have ring homomorphisms, and if M is an R module, then there is a canonical homomorphism of R double dash modules. Okay, so you see the whole idea is that from R module, you have this canonical homomorphism, isomorphisms, taking it to R double dash module. So I think, I mean, the one way of understanding it is that try looking at the right hand side first. So if you have a tensor over R double dash, okay. So see, if you have naturally, since you have R to R dash to R double dash, so naturally tensor product gives you the extension of coefficients, right? So this does make sense. You do have, and anyway, R double dash is an R module. So you have this tensor product, and you can actually show that this is isomorphic to this. So which is, if you can see that this, you have sort of factored through R dash. So that is the main part, and extremely useful as we will see for faithful flatness, and especially for proving the descent properties. We will be using it very, very frequently. Okay, so how to prove this? Once again, these are all canonical isomorphisms. So that means universal property. Do not try any brute force, but I will be discussing the proof also quickly. And another statement is the following, that M tensor, so suppose M tensor N dash, oops, I think, yeah, sorry, it's here. So similarly, for any R dash module N dash, there is a canonical isomorphism of R dash modules and given by this. Okay. So first, actually, basically 1 and 2, you can understand what the difference is. Nothing really. So here you are doing it for R dash, and then here you are doing it for an R dash module. Sorry. Here you are doing it for the R double dash, okay? So which is naturally, you have this ring homomorphism over here, so which is naturally an R dash module, and here you are doing it for an arbitrary R dash module. So that's it, okay? Now, the maps are also given to you, but once again, we have to go by the universal property. There's no other shortcut to it. So let me just show you. So this is going to be the recipe, but the point is, how do you construct this map? That's, so what it is saying, that prove the second assertion first. So for a fixed y dash in n dash, once again, you are basically going to create a bilinear map, which is R dash bilinear, and then that would induce it would induce a linear map. Okay, so for a fixed y dash in n dash, consider this map. This is from m cross R dash to M tensor n dash over R. So this is the definition. This is fine, and this map is R bilinear, and therefore you have R linear map from here to here given by this. Okay, so now this I have again left as E stroke T, that showing that this is an R dash module. Well, essentially it's the same thing. Basically, if you if you follow this discussion where we were saying how to show that if you have an R module, then the tensoring gives you an R dash module. So essentially the same thing, if you have an R dash module instead of R dash itself, then also you have a natural R dash module structure. Okay, so the same proof essentially goes through with the due modifications. Okay, so here do verify this once. Yeah, so if you know that you have this as an R dash module, this M tensor n dash, this is an R dash module. So that therefore the above map is even R dash linear. You can check that easily, and therefore the moment you have a R dash linear map, then that for a fixed y in n dash would create a bilinear map. So you know, I mean, you are trying to give a separately linear map, right? For a fixed y, same trick essentially. And then once you have given this bilinear map, that would induce a R dash linear map from here to here, given by this. Okay. Now you want to show that this map is in fact an isomorphism. Okay. So this map is an isomorphism. Now, how to go about it? That is, you just create the inverse map. Okay. So once again, I have kept E stroke T because you can verify that you can define this map once again in the same way, that you would create a bilinear map first from M tensor M cross N dash to that, and that would take care of linearity, and it will create a linear map from there to there. So some small verifications here and there, please go through it once, and then we can again take care of it if there are some discussions needed, okay, in the tutorial session, or you can post your messages. Okay, so if you take n dash equal to r double dash, then you get your 1 basically. So 2 is the general version, but both these statements will be extensively used. You will see in another 10-15 minutes. Okay. Okay, now this is, you must have studied, when you have studied localization, etc., that you can actually talk about this kind of with respect to, just like you have constructed S inverse R, you can construct S inverse M for a multiplicatively closed set, and you have this, you have the universal property and everything. Okay, so this is a quick recapitulation. I have not, again, I have just mentioned it because these are certain basic facts which will be used every now and then. And here you have a natural flat homomorphism. If you take S to be a multiplicatively closed set, and if you have this ring of fractions, then you can go to this S R to S inverse R. This is a flat morphism. And then there you have the canonical isomorphism of, can somebody say, can somebody tell me whether what kind of isomorphism over what? This will be a canonical isomorphism of which modules?
So S inverse R module.
S inverse R module.
Yeah. Okay. So so you, and this is going to be so S inverse same as an S inverse R module. You can actually see this. Okay. You can see a natural base extension there, right? Extension, because this is a ring homomorphism. And then you have taken the tensor over this and made it an S inverse R module. These are some notations which I'm sure you have seen at some point of time. So we will be using it very often. Okay. So now after these kind of basic things, and do remember we will be calling it the base change lemma, that lemma which I have just now talked about. Okay, so now here actually I have kept some open space because I wanted to add, I will add a few examples a little later. So, so this is the purpose, but let us first understand the statement. Here also there will be an E stroke T that,
Sir?
Yes, please.
Sir, is it possible that suppose we have some non-faithful flat something, is it possible to get some ring such that if we base change, that that will be a faithful flat, such kind of?
I didn't understand the question. If you have a faithfully flat module over a ring R, then?
No, non-faithfully flat, which is not faithfully flat.
And if you have a ring extension of rings, then?
Can we make that extension that so that it will be faithfully flat? Something of
making it faithfully flat. Well, I'm not very sure. I mean, like, I have to think and answer your question. Okay.
Yeah, you are saying that base change, so I thought maybe.
Yes, understood. Yes. So making it so, if you are saying that if you will be choosing that ring suitably, the ring R dash suitably, so that after tensoring it becomes faithfully flat. Are you saying that?
Yeah, yeah.
Okay, okay. Yeah, that could be possible. I mean, like, let me think and come up with a proper answer. Yeah, that may be possible still. But otherwise, getting a kind of faithful flat module out of nothing would be difficult work. Okay, so I'll remember your question and come back to it. Okay. Okay, so yeah, so if you have for an R module M, the canonical map going to this is the maximal spectrum. You have already seen this in Professor Patil's lecture. If you look at these localizations, then this map is injective. And in particular, M is 0 if and only if MM is 0 for all M. Okay, so you're calling it local characterization of flatness, but we don't see flatness here, but we will come to that. Okay. So this also is kind of very standard. I'm sure this kind of thing you have seen before. Now here, it's not difficult to understand, but here I have underlined one portion, which I have said E stroke E. So what is it? So I'm saying that for every maximal ideal, you definitely have an AM, right? This is an, I'm indexing it by the maximal ideal, and this is outside M. Okay, and such that XAM is 0, because here is your X is an M and the image is in 0, is 0 here. So therefore you have such an AM. This follows from the definition of MM, right? Okay, now these elements generate the unit ideal in R. Can somebody quickly tell me why?
Otherwise, it will be contained in some maximal ideal, which is not true.
So, which is obvious that since it is avoiding all the maximal ideals, and therefore that would be containing some maximal ideal. Correct. So, therefore, this proposition actually is nice, not a difficult one, but it's extremely useful. So, I have kept this space out here, and I will come back to it. Okay, but let us use this for the time being. Yeah. Okay. Good. So this is going to be as I said, it's a characterization with respect to localization. So you have a base change R to R dash, that R dash is an R algebra, and N is an R dash module. Then the following statements are equivalent. And N is flat when viewed as an R module via phi. Okay, so that means what I mean to say is that N naturally N is an, don't forget, N is a module here in the if you may allow to call me the bigger ring, okay, over R dash. Then if N is flat as an R module, this is statement 1. Statement 2 is for every maximal ideal in R dash, M dash. By the way, this notation is pretty convenient, that using dash for the ring with dash and no dash for the ring without a dash. Okay, so M dash is a maximal ideal in R dash. Then this localization is a flat R module. So N is flat, then after localization it remains flat. And then for every M dash in maximal ideal in R dash, this localization is a flat RM module whenever M is phi inverse the contraction of this maximal ideal is the one without a dash. Please understand that this dash we will always use for R dash, and for R we will use without a dash. Okay.
Last one will be NM, M dash. The last one, the localization NM or NM dash.
Where are you? Are in condition 3, you mean?
Yes, condition 3.
No, it's all right.
Okay.
Okay. Let me come to that. Let me come to that. Just a minute. Okay. So yeah, that is a problem of making it bigger. You won't be able to see that part. Okay, so here is your condition. These conditions have to be visible, otherwise you lose track of it. So N is flat. This is given to you, and you want to show that for every maximal ideal of R dash, the localization is flat. So basically, what you are doing is you will start with. So let me point out the correct places. So we want to prove that this is a flat R module. This is a flat R module. This is the line. So you start with an injective morphism of R modules, take the tensor, and you want to show that this is injective. Fine. Okay. So now, just a minute. Yeah. Just a minute. Actually, it would have been better. Anyway, I think we will just do with this. Yeah. Okay. So actually, this is pretty inconvenient. For some reason today, I'm not able to scroll it up and down freely. I don't know what is happening really. Okay, anyway, I will do with it. So if you have this injective morphism, now it's given that N is flat, right? N is flat as an R module that is given to you. Therefore, after tensoring, you have the injectivity is retained. But you have already, we have already mentioned if you remember one slide back, that this is a flat morphism, right? When you take the localization, that R to S inverse R, that's a flat morphism. And therefore, you have, this is flat over R dash. By the previous proposition, I mean that. So consequently, using the associativity of tensor products, if you tensor by that, then this morphism, yeah. So this is what I mean. Okay. So yeah, you can see it here. So this is what you want to show, that this is flat. So once you see this, this is n-tensor this. And from here to here, you have this m-tensor n and then rm dash. Basically, you are using the fact that your nm dash is n-tensor r dash m dash over r dash. And this is your m-tensor nm dash. Okay, so now here, here you see two rings, right? Two bases. Now, how can we suddenly write this? I mean, what makes us write this? Can somebody suggest? Is my question clear? What I'm saying is, after tensoring, I have this m dash tensor n and m tensor n, I have the injectivity. And then I want to use the flatness of r dash m dash over r dash. Okay. So I have tensored with this. And now suddenly from this expression, I'm getting this, and this expression, I'm getting this. When you know that there is tensoring over two different rings, are we using something?
Yeah, you use the base change something?
Absolutely. We are using the base change. So so this is exactly what is going to happen every almost at all the places. Okay, so this is exactly what we are using. Just try to remember it a bit. I tried to copy it to some other file. It didn't work. So basically, whenever you have this kind of a situation, then I mean, handling with the middle one, and then you have this r double dash. You have r double dash on the right. Okay. So you can safely sort of get rid of this r dash. That's the whole idea, that you have these, you have two tensor products over two base rings. So you can sort of factor through r dash. That is the whole idea. Okay. And in general, if you, instead of r dash, r double dash, if you have any r dash module, then also it is true. So just keep this in mind. This is what is going to be used all the time. Okay. So I would have loved to keep a copy of this somewhere. Anyway. Yeah. So now that you see that this is the, very slow. Yeah. Okay. So now we are trying to prove 2 if and only if 3. So 2 if and only if 3 is, this is the statement. That given that the localization with respect to m dash is flat, you want to show that the localization with respect to the contraction Rm is flat. So come here. Yeah. So if you have a flat R module for a maximal ideal, yes. So then the map induces a ring homomorphism from Rm to R dash m dash. Is this clear to everybody? That if you have a contraction, m is the contraction of Rm dash. So can somebody quickly tell me how to get this map?
Sir, anything outside M is going to be a unit in Rm dash, because that is going to be lie outside M prime.
So you just use the universal property and that's it. Okay.
Yes, sir.
So once you have that, therefore, again, it's kind of a base extension, right? So, and it is clear that this can be viewed as an Rm module. So this is the justification. Once you have that, then now you want to show that this, retains the injectivity, right? Yeah. So you want to, it retains the injectivity. So the flatness of this over R yields a monomorphism. Now, once again, see, you have your nm dash. Now that was your nm dash viewed as an Rm module you want, and as an R dash m dash module. So what was your, once again, oh, there's some person who's coming in and out. So do remember the statement. I'm very sorry for the inconvenience actually, but no, do not have a solution at least. Okay, so please remember the statement that you had initially the R module, the statement of the R module, and you want to move on to Rm module. Okay, so just keep that in mind, and then vice versa. So here you are. So the moment you have for over R, and now you have to again change the base to Rm. Okay, so that's the idea. So you basically have here again, you just think of this, that you have R to Rm to Rm R dash M dash, right? So the same situation of your base change lemma. And therefore you once again use this, that here you are using the base change. Here you are using the base change. And what is that you are using? You are using the flatness of this one, and that is giving you the flatness of this. And over which ring is the main issue, right? The over which ring, it's now going to be, so here you are tensoring it over Rm, right? So here it was over Rm, and now you have it over R. Okay, is that clear? So do see this once carefully. I mean, I would have, it was essential to show you the lemma once again, actually. Please ask me, where is the question? So first you are using the R module structure of nm dash and the flat flat R module structure. Okay, so you have the canonical morphism, and then you are using the base change lemma here. So that means I told you, right? You sort of kind of jump through this, the middle one. This is the middle one. So R, Rm, R dash, M dash. So this is the middle one. You kind of factor through the middle one. That's what you was doing. So that means you can sort of get rid of it. And then you are back to your M dash and M dash and M dash and M. Okay. M and M dash, actually, what I meant to write. Yeah, this should be M dash, I'm sorry. Okay, so therefore, first you use the flatness over R, and then you are concluding it as flatness over Rm. Okay. Hope it is clear. Just, well, it requires a little bit of, I mean, like what with pen and paper, but this is the whole idea is completely hinged on this, the base change lemma. That's the main thing that is being used everywhere. Okay, and this is what we will be using throughout. Okay. And conversely means you now have to go back to the R module structure statement, that if you assume that 3 is true, that means nm dash is Rm flat, and then you want to show that nm dash is R flat. Okay, so you take a monomorphism, localize it with respect to M, and then again the same kind of argument, that the localization, you know, localization is going to retain the injectivity, and then you have the nm dash over Rm, you have the flat structure, and therefore after tensoring also it is going to retain the injectivity. And now once again you have the base change, which tells you that you can simply get rid of, you can just forget this Rm and then come to this situation. Okay, so it's a very powerful lemma, which is very, very helpful. So that's what you are going to use, and please spend some time on this base change lemma and make sure that you to understand the proof, you do the proof on your own. Okay, so the 3 implies, one is you are trying to go back to the flatness. Okay, so basically this diagram will help you. Yeah, so you start with an injective map of R modules, M dash contained in M, and then after tensoring also it remains injective is what you are trying to prove. And now that lemma I told you, right, this will be useful for us, that given that this is a this is a flat module for every M dash of R dash. So since we have already proved the converse also, so therefore you have this, the injectivity of this out here. Okay, and they are being viewed as R dash modules by N, and the vertical maps are injective, and essentially the same argument as you can see here. Okay, and then you prove that the top row, basically you want to show that the lower horizontal map, you get the injectivity of that, and eventually you get the injectivity of the upper horizontal map. Okay, so this diagram chasing and that use of the base change lemma is what is going to be used for proving such statements. Now let me take you to, please get back with your questions after you sort of have a look at this, or you in fact work it out. That is even better. Okay. So now this is a quick page on tensor product of algebras. This I don't intend to spend a lot of time on this because this anyway is going to show up. So if you have, so first of all, this is the terminology which we use, that when we say that A is an R algebra, that means you have a ring homomorphism from R to A. Okay. Now that has a natural R module structure. Once you have a ring homomorphism, you know that. Okay, so now what do you mean by saying that R algebra homomorphism between two R algebras? So suppose A dash and A double dash are two R algebras. So that means you do have, so look at this diagram, you have two ring homomorphisms from R to A dash and R to A double dash respectively. And then when we say that there is a when we say that there is a ring homomorphism from A dash to A double dash such that the diagram is commutative, that is when we call that there is an R algebra structure or an R algebra from A dash to A double dash. Okay, so this is going to be the definition, and naturally your A dash tensor A double dash over R, this has a R module structure. What is interesting is that it also has the ring structure given by this kind of a multiplication, but no brute force is going to work. So you have to use the canonical procedure. That means using the universal property. Again, you have to show. So I have left it as an exercise once again, that this gives a well-defined multiplication on this. The canonical map given by this gives the R algebra structure on this. Okay, so therefore, first of all, I have to show that you have a well-defined multiplication out here. And then this map is fine. This map is all right, and therefore you will have an R algebra structure. But why is this well defined is the question. So please take care of this, and then we can discuss once again if necessary. Okay. Now these are some statements about the R algebras and the extension of coefficients. That if you have two R algebras, then these canonical R algebra homomorphisms satisfy the following universal property. That, so what is the, let me quickly read it out. That so the green color indicates that it has not been proved here in the notes at least. Okay, but if you want me to add, I can add it definitely, but please spend some time on this. So for any two R algebra homomorphisms, so look at this diagram. It's easier to explain through the diagram. That whenever you have this R algebra homomorphisms, that is from let me say the names correctly. Yeah, so you have from A dash to A dash, this is sigma dash, and A double dash to A dash is sigma double dash. Okay, and this is basically given these phi dash and phi double dash. You want that something that ensures a map phi from this tensor product to A, not as an R module map, obviously, that you know it exists, but as an algebra map. So it has to be a ring homomorphism. So this is the universal property of the tensor product of R algebras. Okay, and then the special case of when you are dealing with the polynomial rings, then this is also very, very useful because we will be using it after some time. That if you are tensoring it with the help of this to over R with the polynomial ring, then it's kind of a natural base change that your polynomial ring over, it becomes a polynomial ring over R dash. So you will have to show that. So I have started with a set of variables. So what I mean to say is that they're algebraically independent over R dash and R. And then if you have this tensor product, this is a canonical isomorphism, and this is also a canonical isomorphism for any ideal A. Now, these are the things which I kind of only stated, but not proved, because we will be using it, but not right now. So let it be here and spend some time. I can again add a proof, and also we can have a discussion on this. Okay. Now I want to come to this, which is, yeah, okay. So this has the last part looks like this. Okay, so this is fine. Now I want to come to, so this is the reason I have just left some blank. So this is which we would like to know. So what is the kind of, did I make it smaller now? Yeah, okay. Okay, so this is what is faithfully flat descent. So basically what we have seen, so let me take you to the last comment. Just a minute. Yeah, here. Yes. Okay, so this is basically what we are trying to establish. That finite type, finitely presented, flat, and faithfully flat. These are some of the properties of a module which behave well with respect to the reverse process of descent for a faithfully flat extension. What does it mean? So that means if you have a faithfully flat extension, so what do I mean by that? I have a ring R, another ring R dash, R2 R dash is a ring homomorphism such that R dash is a faithfully flat R module. Okay. So if I have a faithfully flat ring extension, then what are the properties that with respect to tensor product, the properties are preserved. And if the properties are there after tensoring, then you get back the property to the original one. Okay, in the, if I may call a kind of, if you get rid of the tensor, then whether you get back of all the properties. So that is descent. Okay, so after tensoring, certain properties hold good. What are the properties which can be retained, or rather which you can get back if you detensorize it in some sense? Okay, so this is actually the process of descent, and we will see that these are the properties. First of all, we will establish this, then we will prove some other interesting theorem, that these are the properties that finite type, finitely presented, flat, and faithfully flat, they are retained under this process of descent. So this is the theorem which I'm going to talk about, a bit longish because it has quite a few parts, but you will see the proof again is not extremely technical or anything. It's the base change which will be used. Just a minute, please. Yes, so here you are. So for any ring homomorphism R2 R dash, we have this right exact functor from the category of R modules to the category of R dash modules. And the general concept of descent is that, in some sense, to find an inverse to this process. But anyway, this loose talk is of no use. So let us go to the proposition straight away. So let M be an R module and you have a ring homomorphism. Okay. Now, if M is of finite type over R, what is finite type, by the way? A module, R module of finite type. I think for module, it is probably better to say it's finite.
Finitely generated.
Okay. Then after tensoring, it remains finitely generated. And this is finitely, oops, I'm sorry, this is actually, yeah. So yeah, over R dash. Okay. So yeah, now it is better. Fine. Then the second statement is this, you can easily prove. If M is a finite presentation, what is the finite presentation again? Someone? When you say that M
finite algebra as algebra.
Sorry?
Finitely as algebra, finitely.
No, M is just an R.
There is a short sequence like this, Rm to Rn to M to 0.
So that naturally it is finitely generated also.
Yeah, finitely generated with the kernel is also finite.
Kernel is also finite. Okay, so Rn to Rm to M to 0. Okay, so if you have a finite presentation, then after tensoring, it is a finite presentation over R dash. Every time the base is changing to R dash. If M is flat, then after tensoring, you have flat R dash module. And if M is faithfully flat, then after tensoring, you have faithfully.
Sir, can you speak little louder?
Can I speak little louder? I think I can. Just a minute. Okay, is it better now?
Yes, sir.
Okay, so now this fifth statement is the most interesting statement. Of course, I mean, each statement requires a proof. That's not the point. But point is, now you see, so far we didn't have the condition of faithfully flatness. The extension was just a ring extension. Okay. Now, if you have a faithfully flat extension, that means R dash is a faithfully flat R module via this, then the reverse implications of 1 to 4 hold. So this is exactly what my remark was all about. That if I have, after tensoring, if I have faithfully flat, then the original module is faithfully flat. After tensoring, if I have flat, then the original module is flat. After tensoring, if I have finite presentation, then M is of finite presentation. And after tensoring, if I have finite, then M is of finite type. Finite type if M is a finite type. Now this is the speciality of the faithfully flat extension, and this is the process of descent. That means going back to the original and retain whether that property can be recovered. Okay. So let us see how to prove this. So you can understand that faithfully flat is going to play the main role, but how? Okay. So first let us establish 1 to 4, and then yeah. So 1 and 2 are kind of obvious. So this is the meaning of finitely generated. This Rn to M, you have surjective homomorphism, and this is finite presentation. That means you have this exact sequence, and therefore M is finitely generated, and the kernel is also finitely generated. That's exactly what the meaning is. These are exact sequences. And now if you tensor by R dash over R dash is an R module, then these are all exact naturally, because here there's no problem. And we know that these isomorphisms are true, right? These, in fact, we have established that if you tensor it over R, and then there's a free module, so you get a free module over here. And these are, in fact, isomorphisms of R dash modules. In fact, you have changed the base to R dash. Please make a note of this. Maybe I should have underlined it. Yeah. So yeah. Okay. So these are certain things which you should be careful about, because here every time you're playing with 2 or 3 coefficients. Okay. So you have to be a little careful that these are in fact isomorphisms of R dash modules, and that takes care of 1 and 2, that after tensoring they are both finitely presented and finite type R dash modules. Okay. So this is fine. 1 and 2 are fine. The third part is about flatness. Yeah, now it is better actually. Okay, so the third one is about flatness. So if M is a flat R module, you start with a monomorphism of R dash modules, and we have to show that the tensorized map. So what do you want to show? You want to show that this chap out here, to show that this chap out here as an R dash module, it is flat. So you have started with a monomorphism of R dash modules, and after tensoring it becomes flat. And now I don't have to tell you again. Somebody can answer what is being used here. Look at the diagram and tell me. So in fact, it is written over here. The base change. So you can see this vertical maps. You are getting these isomorphisms that this base change is being used. Okay. And the lower horizontal map is injective, the upper one is injective. So you can see this kind of a similarity, the kind of a pattern in these proofs, that you are using the base change and the diagram chasing essentially, nothing much. But the base change is very, very important, very, very important for all this. 4, this is about the faithful flatness. So you start with, so you start with an R dash module and assume that this tensoring, after tensoring it is 0. Okay, you want to remember, you want to show that this one is faithfully flat. So flatness you have established, you just have to show now that E is 0. Okay, so once again base change, it shows that this is 0. Okay, so hence E as an R module and even as an R dash module will be trivial if M is faithfully flat, therefore, right? So you're basically, so what you are using is that if you have your faithful flatness of M, you have reduced this entire thing to the faithful flatness of M, basically. Is that clear? We are now in the process of going back. Is it fine? Should I proceed?
Oh, yes, sir.
Okay, so now we are in the process of going back. So that means I have a faithfully flat extension of rings, and I know that M tensor R dash. So I want to show that if I have after tensoring as an R dash module, if it has these properties, then the original module should have the property. Okay, so now see how is it. So first we are establishing this finite type, that statement 1. Okay, so there exists a finite generating set of this, because I am assuming this is a finite type, which we may assume to be of this form, xi tensor 1. Is it correct? Anyone has any objection to it? Look at the tensoring, and is this fine that xi tensor 1 will be a generating set?
Yes.
Okay. And over which ring?
R prime.
R dash.
Okay. So now you're trying to show that M is in fact generated by this. Okay. Now, once again, you will understand that this is a very nice standard approach, that what you do is you call it M dash, the submodule of M generated by x1, x2, xn. Okay, you have this injectivity. And then what I mean to say is that you just take M dash to M, you have the injective, you have the inclusion here, and just map everything to 0. Okay. So now this sequence is exact if and only if after tensoring this is exact. Okay, since R2 R dash is faithfully flat. It makes sense? Does it make sense what I have written here?
So it is using the property of R prime being faithfully flat, right?
Oh, without that we don't have 5 won't be true. So we are proving the descent now. Okay, so R dash is faithfully flat over R. That is the assumption. That is the beginning assumption. And now you are using that absolutely. So since you have the faithfully flatness property of this ring extension, and therefore this is fine. Okay, so the tensor sequence is exact due to the definition of M dash.
What is this canonical sequence? M prime to M to 0?
Sorry? Oh, just map everything to 0. So canonical sequence means just map everything to 0. Yeah, right. Okay, so but you want to show that after, so this tensorite sequence is exact due to the definition of M dash, and since this is generated by this, therefore M is generated by x1 to xn. Can somebody tell me, I mean, what exactly do I mean? What is the definition of M dash that makes it the tensorized sequence is exact? So this is to just make sure that you are not lost because of symbols and all this. See, you do have this. Don't forget that your xi tensor 1 generates M tensor R dash over R, right? So therefore, and the map is going from xi going to xi tensor 1. Okay. So naturally, you have the surjectivity. Fine. And now, sorry. You have the surjectivity, and now because of the exactness, you definitely have that your M dash, that also has to be, so your M dash basically, so subjects onto this, if you have this subjects onto this, then you have to have that, this is the surjective map, and therefore M is generated by x1, x2, xn. Okay, so this is kind of takes care of the oops, sorry. Okay.
Sir, could you please explain that part once again?
Which part again?
The tensorized sequence is exact due to the definition of M prime, this line.
Yeah, so M prime is, see, M prime is the one submodule. It's a lot of trouble today. M prime is the submodule generated by xi's, right? Okay, but after tensoring, your M, let me take you to that line. See, what is your assumption? You are assuming that your M tensor R dash is also generated by xi tensor 1. So when you were not tensoring, you did not have that fact, and that is what you want to show, that M is generated by x1 to xn. But after tensoring, you know that this is the generating set, and these are the images of this xi tensor 1s are being mapped onto xi tensor 1, isn't it so? So you definitely have the complete surjectivity. Do you understand? See, before
Yes,
tensoring, we didn't have that. After tensoring, we have started with the assumption that let this generate. So you have the generating set. So therefore, you have the surjectivity, and that takes care of that. The surjectivity at that level, that m dash to m, and therefore you have m dash is equal to m. Fine?
yes, sir. Thank you.
Okay, so now the finite presentation, essentially the same thing, well, but still let me just show you the main part, and so that when you see this, you understand well. Yeah. Okay, so suppose this is a finite presentation, of course, under the assumption that R dash is faithfully flat, and you are assuming that it's a finite presentation, therefore it's a finite type, I mean finitely generated. Okay, once you have already proved that if it is a finitely generated and it under a faithful flat extension, therefore M is finitely generated. Okay, so now you have to show that the kernel part also, that is also your finitely generated, right? So you have an exact sequence out here. Let that map be called phi. Now you tensor, and then you get this as an R dash module sequence. This is exact. And now this I have left is as a small exercise that show that the kernel is of finite type. But can somebody quickly suggest what to do exactly? How can I say that?
So this is same as car phi tensor with R prime.
Yes, absolutely. So again, that so if you see, at least we have now narrowed down to two very important lemmas or whatever you call it. One is that kernel naturally kind of commutes with this tensor product, kernel, image, everything. And also another thing is the base change. These are the two things. Absolutely. So if you use that, then you are done. Okay. Okay. So now the reversed version of 3, that is the flatness. So you assume that, yeah, here you are. So you, oops, yeah, here you assume that M tensor, after tensoring, it is flat over R dash, R to R dash faithfully flat. You want to prove that M is flat over R. Okay. So consider a monomorphism of R module, C dash to E, tensor it. Okay. Now you want to show that this is injective, right? Now R dash is flat. So therefore you can say that this is injective, right? R dash is a flat R module, and you have a sequence of R modules out here. So it's you have injectivity here at this level. And since M tensor R dash is flat over R dash, okay? So the same is true for this map. So once again, you are back to base change. You are almost there. So what you have done is you have used the flatness of M tensor R dash now, which is given to you. So therefore, this retains the injectivity. Again, base change. So you are changing the base with respect to what? You have R and R dash out here. Okay. So therefore, you sort of get rid of this R dash and come to this where R dash tensor over R, E dash M, and then this. Okay. So this is obtained from E tensor. This is obtained from this after you tensor R dash, but R dash is flat, faithfully flat over R, and therefore you have this is injective. Is that fine? So maybe I keep it. Oops. Yeah. What happened? Yeah. Okay. Is this okay? Do have a look and tell me. Okay. Should I go to the next one? So it's basically your faithfully flatness, how R dash is faithfully flat over R is being used here is that. So the moment you have the here, see here especially, look at this, that the faithful flatness of R dash over R ensures that you have the injectivity at this level. But if you want to come to this stage, then you need the base change. So these are the two things which are repeatedly being used. That's it. So these are the, and by the way, this is extremely, extremely useful. So you should understand the base change very, very well. Every time you do that is absolutely essential. Okay. So finally, we are now proving the faithfully flat part. So assuming that faithfully flat is true, for after tensoring, we want to prove that before tensoring you have the faithfully flat as well. So M tensor R dash be a faithfully flat R dash module, and R dash R2 R dash is faithfully flat. We know that M is flat, that you have already proved. You just want to prove the next part, that is after tensoring, if something is 0, remember as an R module, then E should be 0, right? So once again, the base change, what you do is you have to somehow bring this in. That's the whole idea. So if you look at this, now this is in fact so nice that you have it over here, and what you are doing is you are sort of hopping through R dash, okay? So E tensor R dash and then tensoring over R dash, and then you have this, which you get rid of R dash, and this is just E tensor R and then M tensor R dash over R. And this again is just, this is a nice, so you just put the bracket over here and there, so not a problem. So then this is 0, but R dash is faithfully flat over R, and therefore this must be 0. So E tensor M over R should be 0, right? So this is 0 by the faithful flatness, and E 0 by the faithful flatness of R dash over R, and therefore M is faithfully flat. Okay, so the whole idea is that, I mean, you are constantly sort of dribbling with the base change, some amount of diagram chasing, and you have that kernel image thing. So do keep that in mind, okay? And next exercises will follow, but you can see here already there are quite a few checkings that you have to do. So please do not avoid this, because otherwise it will be, in fact, I have one more statement to prove, but it is somewhat longish, so I didn't want to, I want to discuss this today. So I'll do it in the next lecture. So in the meantime, what I would request all of you to do is that, so if I just once again just show you, here the proof is more or less complete, not much to check, but of course you have to verify yourself. But here, this I have not proved, okay? So, oops, just a minute, it will change, slide will change, yeah. So this I have not proved at all, please verify this, okay? So this you treat it as a part of the tutorial sheet, and the tutorial sheet will have many more problems for you to do, for you to discuss, for you to solve, okay? But treat these as exercises. Please do not avoid this. And you will find many more such E stroke T statements, okay? So fine, I think I'll stop here today. I have a little more to say about the descent, the faithful flat descent, and then I will have some more homological algebra to talk about. Any questions?
Yeah, sir.
Yes.
Yeah, suppose I have a morphism, ring morphism A to B.
Yes.
Such that B is a faithfully flat A module.
Yeah.
Now, if we take the spec functor, then what extra information we have in the geometry space?
We will come to that. In fact, it is going to be added in the tutorial sheet, so just wait. Okay, so because Patil has already talked about it, and you know that, so we are coming to that. We will have a very detailed stepwise problem. Okay, so is Joydeep here? Joydeep, are you around?
Yes, sir.
Okay, so Joydeep, that the behavior of the spec with respect to a faithfully flat extension. So we should have that in the tutorial sheet, and also we will discuss it tomorrow. Okay.
Okay, sir.
Okay. So if yeah, what is your name? Soham, is it?
Yes, sir.
Yeah. So Soham, please wait. Tomorrow we are going to have a discussion on this.
Okay, sir.
Yeah, I'll add that.
Sir, and also the content that was covered in the last tutorial, can that be uploaded?
Oh yes, I'm very sorry about it. Actually, we had a plan that the scanned PDF will be uploaded. So once again, Joydeep, please upload the scanned PDF. Actually, we were since struggling with the videos and many other things. This sort of we missed it. Very sorry about it. We will do it immediately after some time. Okay.
Okay, thank you. Yes, sir. And the statement that was being referred to as base change today, so it also follows by using the associativity property of tensor product, right?
No. Associativity property is when you are, I think what you intend to say is that over the same base ring, when you are tensoring, right?
Okay, so otherwise, if I have tensors over two different, then, for example, here, yeah, in this.
Exactly. So that is the challenge. Over the same ring, it's fine. All the niceties happen. But here the challenge is, let me once again show you, and just sort of you kind of keep this in your mind. Just a minute. It will come. Yeah. So here you see you are dribbling between R and R dash. Okay. So you are basically dribbling between three rings. Okay. So you are shifting the base ring. So there, whether you can actually put the bracket over here, because sometimes, some kind of very casual statement will be, I will just put the bracket here by associativity, and then this is isomorphic to R double dash.
Yeah, exactly.
Yeah, not quite. See, but the point is here, your base rings are different. So you would completely have to prove that what kind of, you want a isomorphism over which ring. That is essential, right? That you want an isomorphism over which ring. So this is being, these are isomorphisms over R dash. So that's very important, that why finally you are leading to. And here you don't see R dash in the base ring, right? So
yeah.
Basically you are making an extension of coefficients and eventually getting an R dash R double dash isomorphism. Okay, so this is not the usual associativity which you are referring to.
Okay,
So
got it.
So the same isomorphism will be R module and R dash module isomorphism also, right?
Yeah, of course, yes. So you are basically saying that in the extended setup you have this, yes.
Yeah, and a similar statement was there in Atiyah McDonald saying that if
the idea is all your these smaller rings, allow me to call them smaller rings, all the module structure was called smaller rings are being sort of they are being defined using this map, right? So eventually you are coming to here and defining here and defining.
Sir, I mean, regarding associativity, there was a similar statement in Atiyah McDonald saying that if M is a module, and let's say N be a B module and P be a B module.
Bi-module structure, yes. So basically, you see here. So here, since we have not mentioned it in that form, because that is a little confusing. I find it a little confusing in the sense, rather, this is the situation which you mostly deal with. That you have a ring out here, and you have a ring coming. You have a ring mapping onto this, and another ring where this is mapping onto. Okay, so naturally you can kind of have structure using both R and R dash on R double dash. Okay, so that is I think a little more convenient, and I mean it's kind of direct when you are using it for descent and other properties, faithful flatness.
Sir, actually I have a doubt regarding that statement also that I was mentioning. There, the isomorphism has not been mentioned that whether it's a module isomorphism or B module. So what I think is that it will be both.
It will be a bi-module structure, I think. Isomorphism will have. But
yes,
mentioned there, probably it is.
No, in Atiyah McDonald I didn't find it.
Let me have a check and get back then. Let me have a check. Okay. So yeah.
And sir, in any case, for a bimodule structure over a commutative ring, we can always treat them as a left module, right?
Absolutely.
Thank you, sir.
Okay. So shall we stop today and just stop sharing?
Sir?
So, have a look at the Google Classroom, and we will strongly encourage that you please post your questions, discuss among the groups, but post your questions, and so that it can be more more interactive that way. Yes, please.
Sir, the process of extension and restriction of scalars, are they somehow connected like inverse to each other or something like that?
Not really. I mean, that's the whole idea of descent, isn't it? So, I mean, that's the whole idea of descent, that what are the properties with respect to which we can come back. You can say that it's an inverse process. There will be, what are the you have, I think what you want to ask is that what are the properties for which this descent is not true, right?
Or I mean, I was asking like this: if M is a R module, I am extending the scalars and then restricting it. Is there any connection between M and that restricted structure of M tensor over R prime?
What exactly do you mean by connection? You mean to say in terms of properties, or whether you are getting
any kind of inclusion or isomorphism, something like that?
Restricting the scalar, by that you mean that it has the module structure over the smaller ring.
Yeah.
By that you mean restriction of scalars?
Yeah. Means I am taking M to be R module and then taking M tensor over R prime.
You take M tensor over R dash. Then
yeah.
you naturally have both R. It's an R module structure, R dash module structure, and naturally R module structure.
Yeah.
And then what is the question?
So if I just take the R module structure on this extended ring, is it extended module? Is it somehow means either there is an inclusion from M to this, or maybe isomorphism, something like that?
Inclusion. Why should it? No, I don't see why that is true. I mean, that is exactly what this whole story is all about. That you basically, instead of that, you have the universal property. You have ways to give maps. But what is the best you can say is that what are the properties on tensor product ensures that the properties on the original modular ring, kind of you can get back the origin property on the original module. That is probably a more reasonable question to ask, and that is the whole idea.
But if we are looking at M tensor R dash as R dash module or as R module, then the structure that we are defining is basically the same. So they both are essentially the same in terms of properties, in terms of everything.
Anyway, the R module structure is also what? Via that map. It's always via that map. So there is no, but I think what he is asking is whether you have an injective map from M to M tensor R dash and the injective map as an R module map. Am I correct? Is that your question? Yeah. So, but that how do I know? I mean, like naturally that is impossible, unless of course you have some very special situation. But that is so that's exactly what I'm saying, that your R module structure is being sort of it is kind of getting that R module structure also via the structure homomorphism. But more natural question would be that if you have certain properties on the tensor product, whether you have the same properties on the original module. So that's exactly.
I think, in fact, this will be an injection if R prime is faithfully flat over R.
Yeah. I mean, yeah, I mean, these are kind of, see, you have this injection, rather you have that useful injection that on the product of NMs, right?
Yeah.
Okay, so you know that where it is sitting, and this is kind of which kind of is used. You have already seen that used once. So that is a kind of a more useful place where you would like to see M is sitting as a submodule. Understood? So we stop here. Thank you so much. And once again, just keep a watch on the Google Classroom. You will find your tutorial sheet and everything. Okay.